Okay. So far we discussed single qubit gates, how single qubit gates can be decomposed in terms of sequences of rotation gates, right? And that's an exact decomposition. So that's one way to think about implementing single qubit gates, is if you can do arbitrary rotations about x, y, and z axis of the block sphere, then that gives you a way to do arbitrary single qubit gates, right? Because any single qubit gate, there's a systematic way by which you can decompose it as product of rotations. I showed you around y and z axis, but equivalently you can do this with x and z. In fact, you can do this with any arbitrary pair of axes on the block sphere which are perpendicular. Okay. Now, however, as we were discussing last time, single qubit gates are not sufficient to guarantee universality, right? And universality means that we should have the ability to implement any arbitrary quantum gate, and now that means an arbitrary gate on, say, n qubits, right? Which means any 2 to the n cross 2 to the n unitary matrix, we should have the ability to decompose it in terms of some elementary operations or elementary unitary operations, right? And a key ingredient in that is this set of 2-qubit gates, right? And in particular, the controlled gates, right? And I think I mentioned this last time, that we can think about local 2-qubit gates, which means I would have some unitary U on the first qubit, tensor some V on the second qubit. And then we can think about non-local gates, and this is where all the controlled operations come in, right? So for example, we have the well-known example of the CNOT. And like I said, this is also simply called a lambda of x, because I can equivalently think of this as a controlled x operation, right? Now, what I cannot think of this is this way, right? What I've written out here is identity tensor x, right? This is identity. When I have a wire with nothing on it, that is simply the identity gate, right? So if you want, I can write like this. So this is not the CNOT operation. And we actually wrote down these 4 cross 4 matrices and we compared this, right, last time. And we said that the CNOT cannot be simply expressed in this form. So how can I use this Kronecker product or this tensor product to describe the CNOT? Well, there is a way to do it. There is a way to describe all the controlled operations in the following sense. So it is not as if what is happening on the first qubit is an identity gate, but rather there is some kind of implicit measurement happening of the first qubit. Okay, and what I'm going to say now will also feed into the next point, the final point that I will mention here in today's lecture, which is about measurements in quantum circuits, right? So the CNOT or any controlled operation, you can think of it, you can describe its operation in this way. It is as if the first qubit is somehow being measured, right? And in fact, it's a projective measurement, right? Because what are you conditioning on? You're conditioning on whether the first qubit is a 0 or a 1, right? And how do we decide this for quantum states? We have to do some kind of measurement, and in this case, it's a projective measurement like this. But this is some kind of implicit projective measurement, because we don't know the outcome. Now, if we knew the outcome, then the state would collapse anyway. And that's not what you want, right? Suppose, so note that I'm not saying that this is what is happening. No, this is not what is happening. But somehow, if you think about it, what is happening is the outcome of this measurement is being fed into the second qubit, right? The outcome of this measurement is being used to decide what to do with the second qubit. I shouldn't draw like this either, so that's also not what's happening. In fact, we'll contrast with that very shortly. Okay, so note that this is not what is happening. It's not that this is being measured, in which case this state will just collapse into 0 or 1, the first qubit, right? Rather, it is as if there is an implicit measurement happening on the first qubit, whose outcome is deciding what is happening to the second qubit, right? Conditioned on the state of the first qubit, something is happening to the second qubit. And the nice part is the whole thing is happening in a unitary way. It's happening in a unitary fashion. Now, this means that it is a linear transformation, right? Which means, of course, it does not break superposition. Rather, it preserves the superposition. So the point is, the CNOT or any controlled operation actually provides us a way to do this in general. It provides us a way to condition an operation on the second qubit depending on the state of the first qubit, or actually even vice versa. So I will draw that also very shortly. So instead of saying first and second, let me say control and target. So the CNOT or other control gates provide us a way to do an operation on the target qubit conditioned on the state of the control qubit without having to measure and destroy the state, without having to measure and destroy the superposition, right? So this also becomes a very useful tool in various aspects of quantum circuits. It becomes very useful in quantum error correction and so on, right? So how do we then write this out? It is not, like I said, I've told you what all it is not, okay? I've told you that it's not identity tensor X. I've told you that it is not a projective measurement on the first qubit and X on the second qubit. Rather, it is an operation of this form. So the CNOT can be written like this. Imagine that you don't have a complete projective measurement, but you just have a projection onto 0 on the control qubit. So I'll put label C to denote that this is a control qubit. If this projection gives you an outcome, then nothing should happen to the second qubit. Or you could have a projection onto 1, and if that projection gives you an outcome, then you have to do an X operation on the target. So I hope this notation is clear. Remember, this is simply something like this. It's AI tensor, sorry, it's A1 tensor, oh, sorry, let me put A control tensor B target plus, I don't know, F control tensor G target, right? So it's as if these are all single qubit operations, right? Note that this is not a gate. Just 0, 0 is not a gate, right? It's a projection, okay? But it's as if this, so I'm writing down now C0 as a sum of local tensor products, as a sum of tensor products, not as a tensor product itself, but as a sum of tensor products. And again, this should remind you of how you can write an entangled state as a superposition of product states, but not a single product state. It doesn't factor into a state in A tensor, a state in B, or a state on the control tensor, state on the target, let's say in this case, but it factors into a sum of such operations, right? So this is a sum of tensor products. Okay. So now you can play around with this and do various interesting things, right? So first of all, you can talk about, so let me just discuss a few variants of the CNOT. Okay. So firstly, you can have a flipped CNOT. By which I mean that you flip the location of the C and the T, the control and the target. So instead of simply always having the first register as the control, I can do this, right? So now this becomes control and this becomes target. And mathematically, this would now be written as identity tensor 0, 0, simply because I order, when I write down the systems, I order them like this, right? So plus X tensor 1, 1. Was there a question?
Yes, ma'am. Ma'am, am I audible?
Yeah, sure, you are. Yeah, tell me.
Yeah. Ma'am, you mentioned a statement that it is a kind of an implicit projective measurement that is not destroying the superposition. I mean,
Yeah.
I'm not able to understand it from this sum of tensor product. Could you please explain it?
Yeah, so the 0, 0 is like a projection on 0, right? And the 1, 1 is a projection on the 1 state, right? So now maybe I should just explain the action a little bit with the state. So let me do that here. So now imagine that the input is the state 1, 0. Okay. So then you have to have CNOT acting on 1 tensor 0, right? So now just work it out with this notation, right? So then this becomes what? So it becomes 0, 0 tensor I plus 1, 1 tensor X acting on 1, 0, right? So now do this term by term. So the first term acts on this and gives you nothing, right? Because this is a projection on 0 and this is 1. So this is not going to have any output. It's the second part which is going to have an output. So it is basically then going to be 1 tensor X acting on ket 0, and that is nothing but 1, 1. So the point is, what the first register is doing is it's sampling the state of the qubit, but it is sampling in a way that the net operation is still unitary, right? So if it is 0, 0, it does identity on the second qubit, and if it is 1, it does X on the second qubit, but it doesn't implement independently a projective measurement on the first qubit, right? It's as if you're probing, that there is a way for this controlled operation to probe the first qubit and hence do something on the second qubit. Except now you shouldn't think of this as a time sequenced event, right? We describe it that way, but it's all happening in one shot. And the reason it's happening in one shot is this parallelism idea, right? I have a 2-qubit gate. I can give 2 inputs. I get 2 outputs. It's just that the way these outputs are generated, if you go into the mechanics of it, it is as if there is an implicit measurement happening of the first qubit, and then based on that, something happening to the second qubit. Right? So it is simultaneously probing whether the first qubit is in 0 or 1 and implementing a gate operation on the second qubit accordingly.
Ma'am?
Yeah.
Other words, so we have these projectors 0, 0 and 1, 1, right?
Yeah.
We don't have that in our hardware, but I mean, this is a mathematical way of, capturing the action of to be able to understand what's the ancilla bit condition is, so that we can have a further consequence on the target bit.
Yeah, I mean, I'm not saying that this is what is actually happening, right? I'm not saying that there is something in your hardware which is doing this P0 and P1. But I'm saying that the net action of this unitary operation, however you're going to realize it, and that's a separate question, how is the CNOT actually implemented? And we'll come to that maybe. Like I said, the next 2 lectures, Chandra will talk a little bit about gates on IBM and show you a few things on the IBM processor. But maybe once we resume after the mid-sem, we can briefly discuss a physical example of how the CNOT is implemented. Okay, I could give you an optical example or something. But the physical action is different, right? That is happening in whatever way it is happening. And that you can typically view it as this operation, right? The way we write 0, 0 going to 0, 0, 0, 1 going to 0, 1, etc. I'm just saying that mathematically, the way this breaks down is like this, right? That it breaks down as an implicit projection on the first qubit, which is then coupled with the identity operator on the second qubit, an implicit projection on 1, which is coupled with the X operator on the second qubit. So this becomes, like I said, a useful tool to do this kind of a transformation. There may be several instances in your quantum algorithm or your quantum circuit where you want to do something to the jth qubit conditioned on the ith qubit being in a particular state. So this whole setup of controlled gates provides you a way of doing that. Okay, is it clear?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. All right. So yeah, I mean, yeah. Go ahead.
Ma'am, in the example of this CNOT gate acting on this 1-0 state, just to confirm whether here the first term is vanishing because the projection of 1 on the 0 is 0, nothing, right?
Correct. Yeah. Yeah.
Oh, okay,
Yeah.
ma'am. Okay.
Yeah.
Thank you.
Exactly. Okay. Fine. So let's move on. So I wanted to talk about the variance of CNOT. So you can think of a flipped CNOT. And like I said, the way you would describe it in this Kronecker product notation is now the projections are happening on the control rather than on the target. Sorry, on the second qubit than on the first qubit, right? It's just that if I want to call, in my mind, this is first and this is second usually. Now, instead of this being the control and this being the target, it's just flipped the other way around, right? Nothing new about it. I'm just writing down various possibilities so that you're aware of this. The other one is, I don't know, this is sometimes called a CNOT bar or a CNOT tilde. And the circuit notation for this is like this, okay? It's not a black dot, but a white circle, okay? And the idea is that now the target is going to be flipped when the control is 0 rather than 1. And again, you can visualize such a gate, right? So now this gate operation is going to be 0, 0 tensor x plus 1, 1 tensor I. Okay? And the last bit that, since I'm writing various ways of representing the gates, can you work out for me what the 4x4 matrix corresponding to this is? So in fact, you could do this exercise right here. When I write down this notation for the CNOT, you should check that this is consistent with the 4x4 matrix that we wrote down last time. And how will you check that? You have to write down you know what the matrix operation for identity is, you know what it is for X. You just have to write down the matrix operation for 0, 0 and 1, 1. So remember that these projections have this matrix form. Yes, this is this 2 by 2 matrix, and 1, 1 is this 2 by 2 matrix, right? So yeah, could you just work out what this matrix is? So you sort of see this block form emerging, right? Remember last time we wrote down the CNOT as a block form. So I hope you see that this is nothing but, so when I do this tensor product, so this is simply a block matrix with X here, 0, 0, 0. This is a 2 by 2 block, right? Plus 0, 0, 0 identity, and this is another 2 by 2 block. So then this is now 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay. So this is another non-local gate, another 2-qubit unitary, which is also a controlled operation, except it is a control bar, right? In the sense that the control now, rather than the control having a non-trivial action if it is set to 1, it now has a non-trivial action if it is set to 0. right? Okay, so this was all about the CNOT. Then there are other 2-qubit gates that one can talk. I hope these ideas are clear, the flipped CNOT and the CNOT bar or the CNOT tilde. So this was the first example, which is the CNOT. So I wanted to also briefly mention two other non-local gates. So the second one is a control Z operation, right? So this is often simply denoted with just two dots, okay? Because interestingly, now this is again, so these are all, now we enter this domain of what are called circuit identities, okay? So this is a simple circuit identity that can be proved, which is that the matrix corresponding to this control Z is the same as doing a control Z the other way around with the control and the role of the control and the target flipped, okay? So I encourage you to please check that this is the case, okay? And how will you check? You just have to show that the two matrices are equal. So what is this matrix? Well, this is again, now I'm going to use this tensor product notation that I've introduced. This is 0, 0 tensor identity plus 1, 1 tensor Z. So this is now 1, 0, 0, 1, 1, 0, 0, minus 1. Okay. So please check that this gives you the same as this. Okay. Remember what the notation for this is. We just wrote down the one for control X. Okay. So the control Z is simply denoted with two dots and a line connecting them, because it doesn't matter really which is the control and which is the target. They both have identical action. Both these unitary transformations, the one here and the one here, have identical action on any state finally. Okay. So this is another non-local gate. And like I said, let me just write down an example 3, which is any controlled rotation gate, right? So I could have an Rx, I could have an Ry, I could have an Rz, right? So all of them will be called lambda of Rx or lambda of Ry, lambda of Rz. So these are all now controlled rotations. Okay. Then general controlled unitaries and so on. I just want to talk about one other non-local gate, which is not a control gate. Okay. And this is a very important gate called the swap gate. Okay. And what the swap gate does is it literally just swaps. So this is how it is represented. It's represented as a cross like this. Okay. And the idea is if I have some state phi here and some state psi here, the output should become psi phi. Okay. It swaps. So any phi tensor psi is taken to psi tensor phi. Now, again, this is a state that does something non-trivial across the two qubits, right? So this is another example of a non-local gate, meaning one which cannot be realized simply by two local operations. I cannot hope to do a local operation on the first qubit and a local operation on the second qubit and hope to execute swap, right? It is again truly a non-local gate, and it requires some non-trivial 2-qubit gates to actually implement this. So how would I get to the matrix representation of this? Suppose I gave this to you as a problem. I said, here's the swap. This is the action I want. Now, what is the matrix representation for this gate? How would you work it out? The first step is to think about what is its action on the basis vectors, right? So the first step in understanding any new gate that is presented to you is to understand its action on the computational basis. right? Or the standard basis. So in this case, what is its action on 0, 0? Remains 0, 0. What is its action on 0, 1? What is its action on 0, 1?
It becomes 1 0.
1 0.
Good. What is its action on 1, 0? Becomes 0, 1. So now can you tell me what is this matrix? Can you work out this matrix representation for me?
Ma'am, it is first row is 1 0 0 0. The
Hmm.
second row is 0 0 1 0.
Hmm.
The third row is 0 1 0 0. And the fourth one is 0 0 0 1.
Very good. Yes. So, this is a gate for which you don't even have this block kind of form, right? So it's not even a gate which you can write down the way you wrote down the CNOT as, something here tensor X plus something here tensor I. There will be some kind of decomposition for this gate as well, but it's not so easy. It's not so easy to write down even a sum of tensor product decompositions for this gate. So this is indeed a highly non-local gate, but it is a different kind of non-local gate. Does not belong to the same class as the controlled unitary operations, right? But this will be a very crucial gate, particularly in circuits. So let me just say that this is very important in quantum circuits, especially in translating the quantum circuits to the particular architectures on which they are implemented. So what do I mean by that? Oops, why am I spelling things so bad? So the idea is this, right? So now imagine you have the IBM's 5-qubit processor, okay? So this is an example of a 5-qubit processor on IBM. I mean, I think it has a T structure one way or the other. Now, those of you who are familiar with Rangoli will think that I'm trying to draw some Rangoli out here, but that's not my intention. This basically is how one of the IBM 5-qubit processors looks like. There are 5 qubits which are represented by these dots, okay? And these 5 qubits have exactly this connectivity, okay? So I have these 5 qubits here and they are connected like this. Now you see why the swap is useful, because if I can put some numbers here, I might in an algorithm or in a circuit want to do something between qubit 1 and 2, which is fine. I can do CNOTs between 1 and 2, but when I draw this kind of connectivity, it means that I do not have the ability to do a CNOT, to do rather any controlled operation between qubits 1 and 4, for example, or between qubits 3 and 4, or between qubits 2 and 5, or 1 and 5, etc. Right? So this is where the swap comes in handy. So what you do is you then have to swap the states of qubits 2 and 4, right? Do whatever operation it is you want to do, because 1 and 2 can be coupled, and you can do whatever controlled operation you want between 1 and 2, and then re-swap qubits so that qubit 2 becomes 2 again and 4 becomes 4 again. And swap provides you a nice way of doing this whole operation unitarily again, right? So it's again linearity preserving, it's a linear transformation, and it's unitary. Of course, please check that this is unitary. right? But otherwise, you can take my word for it. And so this is the advantage of the swap operation, right? And it becomes, in fact, very useful and very necessary in various quantum architectures. So this is one example of an architecture. There are other architectures, for example, on IBM, which look like this, right? Where your qubits have some kind of ladder structure. But nonetheless, you again see there's a problem in the sense if this is 1, 2, 3, 1 and 3 cannot be coupled, right? 2 and 4 cannot be coupled. So again, the way to actually get to, if you want an all-to-all kind of coupling, or if you want to be able to do arbitrary operations across different qubits which are not necessarily connected or coupled in your architecture, then the swap provides a way of doing this unitarily. Okay, I hope this idea is clear. And the last thing I wanted to talk about is what are called circuit identities, and I will use the swap to give you the first example of a circuit identity. So how is the swap realized in most architectures is as follows. So the swap, it turns out, is actually realized by a set of 3 CNOTs, like this. Okay, so it turns out that the swap can be realized by a sequence of 3 CNOTs. So again, this is something, so this is what I mean by a circuit identity, right? That and the reason again this important is again from an implementation point of view, right? My architecture does not have a natural swap gate, but I have the ability to do a controlled bit flip. So can I use the controlled bit flip or the controlled NOT to do a swap? Well, this is how you do it. Second circuit identity. My architecture has the ability to do a control NOT, but it does not have the ability to do a control Z. And let me use this notation itself for now. So how will I do a control Z from a control NOT? I think you should be able to tell me this.
Ma'am, had a mod on the target, then a controlled knot, and then again had a mod on the target.
Okay, very good. So the idea is to basically make use of the Hadamard gate. Okay, so we can first note a single qubit gate identity or circuit identity, which is that the Z gate is nothing but Hadamard X Hadamard. So as matrices, I will write this as Z is equal to HX H, right? So you can write down similar identities. You can of course write down that X is again H Z H. What is HY H? Again, this is something you can work out and tell me. But now that you have this sequence, you can then use it here to decompose the control Z in terms of the control NOT and other single qubit gates. Which are the other gates? 2 Hadamards. So indeed, this is what we need to do. You do a CNOT because that may be the only non-local gate that your architecture can do. And then you do the Hadamard to the left and the Hadamard to the right. And this gives me a way of doing the control Z. Of course, you can also do the reverse. There are architectures where the control Z is the natural gate. The control NOT is not easy. So then you put the Hadamards onto the control Z, and that's how you get a control NOT. Right? So these are all various ways of playing around, combining the gates that we have to get to the gates that we want to, right? What is Hadamard? Why Hadamard? Single qubit sequence of gates. What does this give me? Okay, so the claim is that this gives me a minus y, and I encourage you to go check this. Okay, here is another kind of gate identity. Suppose I have the control NOT and I do Hadamards on both the control and the target. Okay, then what do I get? It turns out, and this is again easy to show, you just have to work out do the math a little bit on what each step, what it is doing on the computational states, and then you will see that actually this gives the so-called flipped CNOT. Okay, so obviously I'm not going to sit and work all of this out. This is for you to work out, but you now have all the tools. You know how to check this. You have various ways of doing this. So for example, to see this, right, you can simply use this notation. So what does it say in this notation? It is saying that this is equal to 0, 0 tensor I plus 1, 1 tensor HXH, right? And you see this single qubit gate identity then gives you this 2-qubit identity immediately. Okay. All right. So no questions so far, I guess. So I encourage you to check this, and you can show these circuit identities either by using this Kronecker product notation, or you can use the full 4x4 matrix notation, or you have to show the equivalence by acting this on the computational basis states. The only thing to keep in mind is when I have a sequence like this, actually let me write down maybe a sequence like this, right? So when I have something like this, remember, what is a sequence of matrix operations now?
X times S.
X time S.
Yeah, so the way the gate is going to act on a state psi is the S gate is going to act first and then the X gate. Okay, so if I want to call this some operation U, then U is XS. Okay, so when you do the matrix multiplication, this comes first in the sequence, so to speak, on the left, and this gate comes next. Is this clear? So please remember this time ordering here. Okay, that this is the time ordering of the gate operations, right? That when I apply gates in sequence like this, of course, this is the gate that gets applied first and this is the gate that gets applied second. But if I want to do the matrix version of this gate, then it is not S times X, but rather it is X times S for this reason. Please keep this in mind. Please watch out, because this is a common error that people often do when you're trying to deconstruct circuits. Okay. So this is the sequence and this is the sequence here. Okay. All right. So the last thing, like I said, I wanted to talk about measurements in quantum circuits. Questions so far on all the 2-qubit gates and gate identities and circuit identities and so on? Okay. So the last point regarding circuits and gates is what is often called this principle of deferred measurement. And this relates to what we just already discussed with respect to the CNOT, that these controlled gates actually provide us a way to push the measurement to the end of a circuit, right? So the idea is that measurements can always be moved to the end of a circuit by making use of controlled operations. So, and like I said, the idea is this, right? So somewhere in a circuit, if I want to do something on this qubit, conditioned on this qubit being 0 or this qubit being 1, then all I need to do is to do a controlled there could be other qubits in between or whatever, but all I need to do is this controlled operation here, instead of having to do a measurement and then use that. So let me write it like this. So the idea is this, right? So suppose I have qubit I in some circuit and I have qubit J, and I want to do something. I want to do this gate operation U here, okay, conditioned on something happening here. So instead of doing this, what is this? This is a measurement, okay? And then this measurement has a single bit outcome. And let me call that as C, okay? So C is the outcome bit. It's 0 or 1. That gets fed into this. And so this is then written as U to the C, which means it is identity if C is 0, because it's U power 0, and it is U if C is 1, right? So this is one way of writing this, right? But this entire thing can now be replaced by this, okay? And this measurement on this qubit, if at all it is, in the end being measured, or if, the state is being collapsed in the end, can simply be moved to the end of the circuit, right? So this is the so-called principle of deferred measurement, and we can actually use this to write down a different kind of teleportation circuit. The way we describe the teleportation protocol is as a kind of communication protocol between two parties who are located spatially separate locations, right? Instead, we can talk about a teleportation circuit which can happen within, let's say, a quantum device. So the idea is not to now communicate information across two distant parties, distant, whatever they're located, far apart and so on. Rather, the idea is to simply transfer the state from one register to another register within my computer or within my circuit, right? Without having to measure and reconstruct and so on, right? So the teleportation idea gives you a neat way of doing this. So remember what we had. We had this CNOT. We had this Hadamard here, right? And then we said in the usual teleportation circuit, so this is the state which is to be teleported. These two qubits are in an entangled state, right? So we said that earlier we had put measurement here, and we said that that classical outcome is now communicated to this qubit which is there in Bharat's lab, etc., right? Now I'm not going to do any of that. I'm going to say that you simply are doing two controlled operations, okay? You're doing a controlled X operation with this second qubit, and with the first qubit, you're doing a control Z operation, right? Now, in the end, you may measure these two qubits. And in fact, this measurement will tell you, well, it'll just tell you exactly what happened in these locations, right? But that's not information that you're immediately using, because that information has already been transmitted to the third qubit via this controlled operation. So you can defer this measurement to the very end of whatever operation you want to do, the very end of the circuit, wherever that end may be, right? So you don't need to really destroy these qubits, right? And without having destroyed them, you have achieved your goal, which is to have this qubit in the state side, right? So this is a modified teleportation circuit, one which can be used within a quantum device to teleport a state across registers, right? To teleport a state from one location in your device to another, right? And this uses only the control X and the control Z, right? So is this idea clear? This idea that you can use the controlled operation to basically push your measurement to the very end. Rather than having to do this in the middle of a circuit, you don't have to measure the qubit, communicate that information, and that's once you measure, all that you're left with is a classical bit worth of information, right? And then to having to communicate that to a different location, etc. So that needn't happen, right? Instead, you can use this framework of controlled gates to realize the same thing. Okay, so maybe one other thing, since I have a couple of minutes more, that I will mention is the Bell basis measurement. Have you all looked at assignment 2 yet? It's due in a couple of days, right?
Yes, yes, ma'am.
So have you solved the Bell basis measurement question? There is a question on this.
Yes, ma'am. Yes, ma'am.
Okay, good. So then you will realize, so this is just to point out that what we have here in the teleportation circuit, this part is actually realizing what is called a Bell measurement, right? So, and this is basically, the idea here is to show that you can measure in an entangled basis by simply using the gates and the measurements at your disposal, which is CNOT, Hadamard, and single qubit measurements. Right? So what is a Bell basis measurement? Remember, you have these 4 entangled states. Now, these 4 states are orthogonal. So again, you must check this, and they are normalized. And this is a set of 4 states. So obviously, then they form an orthonormal basis. Right? And if these 4 states form an orthonormal basis, the question becomes, can we measure in such a basis? Because any orthonormal basis can be converted into a projective measurement of some form, right? So can we measure in such a basis? So the answer is yes, and that is indeed what this circuit is achieving, and that's what you've been asked to show in your assignment, I think. So this the idea is that you will get 2 outcomes here. There's a bit 1 and there's a bit 2, which belong to 0, 1, right? And depending on what values you get for B1 and B2, you should be able to map distinctly to one of these 4 states, right? And that's what you need to check. So the 4 values of this combination B1, B2 then leads to maps distinctly to one of these 4 states. Okay. All right. Let me stop here. And like I said, on Thursday's lecture, we will have Chandra talking about the IBM quantum processor. And by Friday's lecture, you should be able to have your own account on the IBM processor and start to implement some simple gates and circuits, right? So this pretty much covers your midterm, mid-sem syllabus. I've not really given you the universality argument yet, but I have given you pointers to say what are the ingredients that go into it, right? So maybe in Thursday's class, I'll briefly talk about universality in the beginning, and then we can have Chandra do the lecture. Okay. Questions?
Ma'am, in this new teleportation circuit which we made,
Yeah.
what is the role of measurement exactly? Because previously, before the measurement, no data was actually, no information was transferred to the other state, right? But here
Yeah.
it seems the information just comes into, means the third qubit, whether or not we measure, means get the measurement outcomes or not.
Yeah, so the point is that the role of these measurements is to kind of ensure that you're not violating a no cloning kind of argument, right? So the collapse of these 2 states, right, is necessary in the end, okay? But it's just that it doesn't have to happen in the sequence where you collapse and then you convey the information here. It can just happen in this way, where you just use these control X and the control Z gates, and that then already achieves the desired transformation for you, right? So if you go back to the so if you go back to the state that we had written down, the state, I think, just before, so if you go back to, I think, the state here, right? We had written the state out in as I don't know, the first 2 qubits. So I think these were called A1, A2, and B, right? And this was written as 00 A1 tensor something here, 01, etc. Right? If you, I don't know if you remember that we had that way of decomposing the state, right? Now, the point is that these controlled operations do finally lead you to this. But if you want to complete the teleportation scheme in some sense, then this measurement is what will collapse you to one of those 4 states finally. Otherwise, you are in this. Okay, so let me state this now clearly. Okay, so this measurement is necessary. I should, maybe again at the beginning of next lecture, I should emphasize this. This measurement is necessary because otherwise you will be in a superposition state of this form. Okay, I'm going to write this in some abstract way. I hope you'll understand this, but basically, tensor by ij. Is this clear? Amog is the one who asked me the question.
But ma'am, then when we measure it, it will be in one of the states, right? So it will be
Correct.
either in 511
No,
or
the point is that this phi ij will be modified already. So this was in the earlier teleportation circuit. Now that I've done this controlled operations, what happens? I will now have, I mean, you can put the control gates here, right? So I will have x raised to I or z raised to j phi ij or something like this, right? So this is what I will have still, right? So I will
But
have a
then-
sum of these 4 states. The controlled operation acts across the superposition, right? Remember, there's a superposition here, and this acts across the superposition. Effectively, this state is now in psi, and you can proceed to do whatever computation you want to do with this. But I'm saying if you want to view it as a teleportation exercise, where your exercise is merely to get this state out here and stop. When you stop, you have to do this measurement. That's what I'm trying to say. Is that clear?
I'll think about it maybe.
Yeah,
I'll
like I
get
discussed
back to
this in
you.
the beginning of Thursday's class. The point is that until you do this measurement, and it's good you asked me this question. When I was discussing, I thought I should, I'll clarify this on the beginning of Thursday. Until you do these measurements, you are still in some superposition of these different possibilities. Although you have done the correct controlled operations, and like I said, the state will be what you want it to be here. But it is not, I mean, it is not the end of the protocol, right? If I want to end the teleportation protocol, then I exactly want psi here. I don't want psi to be hidden in some superposition form, which is what it will be in unless these measurements happen. Okay, so think about it, and I can write it out in the beginning of the next lecture.
Okay, yes, ma'am. Thank you.
Okay. Okay, let me then stop recording, and I'll see you all on Thursday.